we will say that the density is homogeneous. Okay? It does not depend on the space position, at least initially. But if it's constant initially, with this evolution, it will be constant for all times. Okay? So we will see, we will here say that the density is homogeneous. So rho here will be a constant. Last conservation law is conservation of momentum. I mean, last for our purpose. Okay? So conservation of momentum now. Yes.
Is there any model that studied without like homogeneous density up to now? Because I think like Lewis is studying something with like different.
Yeah, so this is, I mean, for classical Euler and Navier-Stokes, you must impose this simplifying assumption. But many people still keep this equation, or you have compressible models in which you need this equation. Okay, so this is an important equation, but it's somehow hidden in the Euler and Navier-Stokes model where you have this homogeneous assumption. But it can be as soon as you lose homogeneity, as soon as you lose incompressibility, then it becomes a crucial equation.
Excuse me, so here do you mean the density is constant in time, not in space?
Homogeneous means constant in space. So initially, rho does not depend on x. But if it is constant in space initially, it will remain constant in space for all time. Okay? Yeah, by the way, feel free to ask any question. Okay, so the conservation of momentum now. Again, I start from my arbitrary volume, V, and I will say that the variation of momentum inside the volume is d over dt. This is my transported volume, right? X of t and v. And what is momentum? It's mass times velocity. So you will recover rho times u. And conservation of momentum is saying variation of momentum is given by forces on the volume. Okay, so this should be forces on V. And usually you distinguish between two kinds of forces. There are forces at the surface of your volume, and there are forces inside the volume. Okay? So these forces in general mechanics can be written as the surface term integral over the surface of sigma n. What is sigma? Sigma is called, so it's a matrix, sigma ij. This is a symmetric matrix called stress tensor. This is general mechanics. A symmetric matrix, this is called stress tensor. N is the normal vector at the surface pointing outward. So you have this surface force, and you have then some kind of volume force. Like gravity, for instance. Like gravity. The fluid has some kind of mass, and so it can be gravity, it can be anything you want in your model. Okay. Then you use Stokes' formula. Okay, Stokes' formula tells you that the integral of sigma L over the surface should be the integral of the divergence of sigma over the whole volume. And divergence of sigma that's the divergence of the matrix, so that's a vector. So that's the sum of tj sigma ij, I between 1 and d. So you have again a conservation expressed in integral form. You can compute this time variation like before. The dt can enter into the integral, right? And you end up with an equation which is so the conservation of momentum in the end gives you an equation which is dt of rho u plus u dot grad scalar operator applied to rho u minus divergence of sigma equal f. So then the question is, how do you define, or what expression do you use for the stress tensor? So what expression for sigma? That's a modeling issue, right? We are still trying to derive some kind of model. We express conservation laws, but at this point we need to specify the kind of forcing that is exerted inside the fluid. So you have two different kinds of models. One will give the Euler equation, the other one will give the Navier-Stokes equation. So, for example, you have ideal fluids where you neglect viscosity. When you neglect viscosity, you say that the only forces on a little volume of fluid are normal forces, okay? And you will say that sigma will be proportional, sigma n will be proportional to the norm. So sigma will be a multiple of the identity. Okay? And so you express that you have a normal forcing on a little volume of fluid, and this forcing is measured by some coefficient here, P, which is exactly the pressure. Okay, so P, that's a scalar function. It depends on the time, it depends on the space position, and it's the pressure. So that's ideal fit. You neglect any other effect. You just focus on the normal forces, the pressure. But of course, then you have more elaborate models. And for instance, you may want to take into account viscosity. So for a viscous fluid, you must add something to sigma. Okay, so I don't want to detail too much. Let me just say that you don't just take sigma to be a multiple of the identity. You must add something, add another matrix that takes into account viscosity. So then you can discuss the matrix, okay? But let me be vague. You add something that you find in the literature as the so-called Newtonian tensor. Okay, so I don't want to detail the expression, but I just want to say that you need to add something to account for viscosity. So at the end of the day, you get the Euler and the Navier-Stokes equations.